Analysis of the Ryugu sample recovered from the Hayabusa-2 mission has revealed an uncontaminated window into the building blocks of our formative solar system. USQ's Dr. Jonti Horner beams in to discuss.
This is a Trekzone conversation.
Well, Dr. Horner, thanks for a little bit of your time to have a Trekzone conversation this morning.
It's an absolute pleasure. Thanks for having me.
Talk us through the basics of what the sample has yielded to researchers, if you please.
Well, it really reveals the value more than anything else of going there and getting something and bringing it back. So absent these kind of sample return missions, we study objects elsewhere in the solar system in the lab if we can get our hands on them by finding meteorites. That's essentially what we do. So we go out all around the world and pick up rocks from space and analyze them. If we're really lucky, those rocks are things we've seen fall. They've come through the atmosphere, we've seen the fireball, we pick them up, and then we know they've been on Earth a very limited amount of time. But in most cases, these meteorites people find have been on Earth for a long time. And what that means is that the Earth alters them, it interferes with them, it changes their chemistry, which when you're looking for things that are incredibly rare, let's say you're looking for evidence of the building blocks of life, or you're looking for evidence of water in these things, it's really challenging to do that with things that are on the surface of the Earth, because if you find something like that, you've got the question of, was it really from the meteorite, or was it something that is contamination from its time on the surface of the Earth? So those kind of studies on Earth are really challenging. And yeah, we've got kilograms of meteoritic material that we found, and it's really valuable, but there are limits to what you can do with it. The flip side is what the Japanese team here have done. They've sent a spacecraft called Hayabusa-2 to an asteroid called Ryugu, flown there, they've landed on the surface, which is an incredible technological achievement, picked up a tiny sample, left a little explosive, flown away and hidden around the back of the asteroid. Explosive's gone off and dug a crater. They've flown back around, landed in the crater and picked up another sample. And they've done that so they can get to the inside of the asteroid, essentially. And then they've brought it back home and dropped it in December 2020 at the Woomera Test Ranges in South Australia. Now, all of that effort, hundreds of millions of dollars of spacecraft traveling for a number of years, got 5.4 grams of material. And that 5.4 grams of material doesn't sound much, but it's so incredibly valuable because we know that it is pristine and uncontaminated and hasn't been on the Earth. So therefore, anything you find in it is really the story of that lump of debris, that sample, those two samples. Now, this study here is the first time we're getting really hard science published from those results from those samples. And this group got given something like 125 milligrams of that 5.4 grams, of which they used 95 milligrams for this sample. So it's something like 1/50th of the sample has now been used to get these results. That's how painstaking people are being. What it has shown us is that this object, or rather the material we've got in our hands in the lab in Japan, is some of the oldest material ever found. It's the most pristine, oldest solar system material we've ever had our hands on. It formed within just 5 million years of the solar system beginning to form. So the Earth wasn't around at this time. In fact, the Earth was just a twinkle in the sun's eye at this point. This sample formed that early, but the really astonishing thing for me is it formed in water. It didn't form in the vacuum of space, but instead it was bathed in water, and it was water about body temperature, the same kind of heat I've got in my body at the minute, 37 degrees centigrade plus or minus 10 degrees. So it could have been 27, it could have been 47, but 37 is the most likely. This thing formed in water. It has not since been heated higher than the boiling point of water or slightly higher, and even then only briefly. So it's incredibly pristine. It's the oldest material we've ever had our hands on from the solar system. And it formed wet. So it tells us a story here of the history of Ryugu, because Ryugu is much too small to have liquid water. It's tiny, it's only about 900 meters across. So this stuff obviously formed in a bigger object, one that must have been hundreds of kilometers across. Very early in the solar system's formation, this would have been like a proto-planet. One of the pieces that, if they were lucky, went together to form the planets. If they were unlucky, got shattered, smashed, torn asunder. And that's what happened in this case.
Now, going and collecting is critical in understanding the formation of the solar system. As you're talking about there, Ryugu was so close to the formation of the solar system. And if I understand the science behind this, the composition of this asteroid is very similar to the outer layer of the sun. As you're saying, it was formed, or the sample was formed in liquid water. So, what does this tell us about the early solar system?
Well, it gives us a window into what was happening at the time. And my apologies for the bingle there, but there's always something goes off in the background. You know what it's like.
Absolutely.
It tells us a lot about that period in the early solar system when the planets were forming. The fact it is so similar in composition to the outer atmosphere of the sun is part of what tells us it's so pristine. The planets, the debris, asteroids, and comets all formed from a cloud of gas and dust, which was exactly the same material from which the sun formed. Now, the sun incorporated a lot more hydrogen and helium because it had the mass to hold on to it, essentially. Whereas something like Ryugu didn't get that, but it incorporated everything else in the same quantities that the sun was getting, without processing, without preferentially accreting some materials over another. So that means it's very young, very pristine. And part of the way that they tell that is looking not just at the composition in terms of the elements, what we call the elemental abundances, how much, let's say, carbon to nitrogen there is, for example. But they actually dig further and they'll look at the isotopic abundances. So they'll look at the different isotopes of the elements and look at the levels of the different isotopes there. And that tells you something about the history, because if you have been, for example, superheated, that can reset the clock on some of the radioactive behaviors that transfer one isotope to another, or it can reset the clock in terms of which isotopes are trapped in certain compounds. So heavy hydrogen in water versus normal hydrogen in water, things like this. And so that gives astronomers something of a clock as to where in the formation of the solar system things happened. And in this case, all of the signs point to this being ancient, pristine. And remember, this is only 1/50th of the sample they've used, actually a bit less than that. So this is the first step in a journey where people are going to be using the rest of the sample. Informed by this, getting these results gives you an indication of what else you could expect to find and what else you want to look for, which then directs that future research. So it helps them figure out what to do with the rest of it. And some of the other results are coming out at about the same time. I saw at the same time this paper was published, another result coming out from the Ryugu samples, saying they'd found now more than 20 amino acids in these tiny little few grams of sample, which are the prebiotic materials, the building blocks of life. It's not life, but they're the compounds that lead to the development of life. And so this is adding weight to the fact that places like the Earth will have got a significant amount of our, what we call volatiles, things like water, things that can turn into gas in space and be lost. We'll have got a significant amount of those volatiles from the impact of asteroids like Ryugu and the object that Ryugu was before it was smashed apart and reaccumulated. But it also tells us a bit that these objects really could have delivered the things that are the base building blocks of life that could actually have led to the fact that we're here having this conversation right now.
Just absolutely incredible. Not only is Ryugu a carbonaceous chondrite, not only does it have this sample of the sun's atmosphere, also amino acids are being discovered as well. I think what's incredible for me as a technically a non-science person is the fact that this is all coming from 5 grams of this asteroid. And beyond that, it took us exploding a part of a chunk of the asteroid apart, flying there not only as a first achievement, but blowing up a little bit of it, coming back, collecting it, taking it back to Earth. So many steps, so many milestones in all of this. For 5 grams, a lot of people would look at that and kind of scoff. But Dr. Brad Tucker, our Talking Science co-host, did talk about it at the time as that can yield so many research projects just from those 5 grams. And Hayabusa-2 is on the way to another asteroid. It's 2 years into an 11-year mission to get there. So there's still time to work out exactly what we want to be studying, what further we want to be studying in the solar system.
There's always much more to learn. I think going into the future, it's informative on many levels. You've got the sheer scientific curiosity of it, but it's revealing as to why governments like the US, like Japan, because the US, of course, has got its own sample return mission, the OSIRIS-REx mission that went to Bennu. It's why governments put so much money into this is a little bit because of the scientific wonder, but it's mainly because of the technology you develop. NASA is incredible. NASA has been hugely funded. And people often say to me, why are we funding this? 5 grams from an asteroid, what's that going to tell us? When we could put that money into curing cancer or whatever. But the thing is, if you invest in spaceflight, if you invest in this kind of exploration, you inspire the next generation of scientists, which is priceless, hard to value. But you also generate the new technology that goes into all these other disciplines. And, the take home from that for me is when you look at the statistics, since NASA was formed, it has returned $10 for every dollar of investment every single year as a minimum. So a 10-to-1 return on investment. That's why governments put the money in. And what it leads to is this development of technology that then trickles down into other areas. So, I've got a, generic fruit-based phone here. Should hide the logo, not product placement. That phone takes pretty good photos, except it actually doesn't. It takes absolutely catastrophically terrible photos that are then turned into good photos in software. And the reason you can do that has its origins in astronomical research and this kind of technology. The optics in there are terrible, but they're reproducibly terrible because every phone that's made has the same flaws. So the software can convert a blurred hall of mirrors image into a really nice picture. And that's just one of the examples of the kind of things we get with this. And that's where this spaceflight's taken us. The other thing that this really reminds us is that you get so much more science out of being able to have something on Earth and analyze it than you do from just taking pictures and going places. And we go to Mars, we send these rovers there, they do incredible work. But I've often heard it said that one human geologist put on the surface of Mars could learn more and achieve more in one day than the rovers have done through the history of the exploration. So that's another part of the push to send humans out into space and also to return samples back to us. The third place that I think missions like OSIRIS-REx, like Hayabusa and Hayabusa-2, these sample return missions, where they come in is they're also tied very intimately to the commercial future of the human race and also to our ability to protect ourselves. In terms of the commercial side of things, going to an asteroid, picking bits up and bringing them back to Earth is essentially what you'll need to do for asteroid mining. I mean, it's a bit more complicated than that. You'll probably want to do processing there, but it demonstrates that in principle, we've got the control to do that. We can go there, we can pick something we're interested in, we can return it to Earth. That suddenly opens up a huge wealth of possibility for resources, for off-Earth mining, for taking some of the more polluting things we do on Earth and putting them in somewhere where that pollution can't harm us. And at the same time, returning huge amounts of money for wealthy individuals, because that's usually what drives things, unfortunately. But it also is the first step in taking matters into our own hands, because if we can get there, well, that means we know the orbit of the asteroid and its position incredibly accurately, which is what you need to do to predict whether this thing could hit us at some point in the future, whether it poses a threat. But beyond that, if it does pose a threat and you want to deflect it, what do? Well, you don't send Bruce Willis there with nuclear weapons and blow it up, because that would just send shrapnel our way. What you do is you land there, deflect the asteroid by possibly digging bits up and throwing them off into space and having it recoil. So I throw something your way, I recoil backwards. I throw something your way again, I recoil backwards. We've just done that essentially. So all of this kind of ties together. So on the one hand, and probably the most important at the minute, the key story is what we're learning from the Ryugu samples. But I guess what I'm trying to get across is that this isn't just pure science. To the people who are in the lab analysing the samples, it is, but from a kind of broader human perspective, this really speaks to a lot of things like planetary protection, keeping ourselves safe, like the possibility of commercial off-Earth mining, and also to the possibility of human exploration of the solar system down the line. So I think it's a really interesting thing that we're opening a door into an incredibly beautiful place that we've never been, and that's the future we get to explore.
It is incredible. I love when scientists get excited about space stuff and the things that we're learning as well, and constantly learning. The things that we thought we knew are often getting challenged, and we're finding new things out. I think incredibly, we're learning about the early solar system. Jonti, I really appreciate your time on today's Trekzone conversation, and looking forward to more discoveries from this Ryugu sample.
Absolutely. I'm just really excited to see what the future holds. Thank you so much for having me.